Good morning, everybody. Thanks a lot for being here this morning for my thesis presentation titled Flying Past Reality. So I'm just going to get right into it. So to get things started, we're going to start with the motivation behind the study and all of the work that I'll be presenting today. So I'm going to categorize it into three broad motivators. The first one being cybersickness in VR. So as we all know, it's a pretty prevalent problem in virtual reality. Almost 65 to 75% of users experience it. It's a huge risk to like user safety and one of the biggest barriers to VR adoption, since people just end up getting sick and not really experiencing as much. The second motivator, and a pretty big one, is just exploring the realm of like 3D flying interfaces. This includes like extending established principles for ground-based locomotion to 3D flying and tackling all of the challenges that come with the sixth degree of freedom motion, which usually also entails like heightened cybersickness effects and disorientation. Um, this mostly involves balancing also precise movements with large scale traversal, because to offer a range of experiences in VR. And finally, user experience factors, which we want to explore further into like learnability and usability of like novel interfaces, and just the effects of other factors like fun and competitive task design into like engagement, cyber sickness, and also cognitive load. So with that established, I'm just gonna get into my research question. This is an overarching research question. The paper covers it in detail, but mostly we're covering how do traditional VR locomotion techniques such as teleportation and continuous motion compare to novel approaches like the HyperJump, and especially in addressing motion sickness, immersion, performance, user preference, and during 3D flying tasks. In addition to that, we also look at factors such as user enjoyment, gamification elements, and just like ease of learning, and how all of this works out in extended use of these interfaces. So yeah, with that out of the way, I'm just going to introduce what is the hyperjump. I've been talking about it the whole time. So the hyperjump is a like novel hybrid interface, initially ideated as a ground-based locomotion system. And the concept and the goal was to mitigate cyber sickness while also allowing for large-scale traversal. So the video I'm showing here is from Ashu Adhikari's work on the interface early on, which was primarily dealing with ground-based locomotion. The key factor of this interface is that it's completely parameterized and customizable. So like I have over here in this graph, you can see that the way the hyperjump works is that it implements continuous motion in this range of like slow speeds, so similar to walking speeds. And after a certain threshold velocity, it starts implementing discrete jumping, as you can see here. So you start jumping forward in bursts and have cool-off periods that maintain the optical flow. So by doing this, Ashu's work before has established that this reduces cyber sickness, it enhances spatial awareness, and it successfully balances speed and precision for large-scale environments. Unfortunately, this work was limited to 2D locomotion at the time, and it wasn't designed for 3D flying, which is where we'll be taking this next. So we started this off with just exploratory studies, starting at the SIGGRAPH 2022 conference. We ran about 260 participants that were transient, so they were coming and going. They didn't exactly go through the entire study, but it was good enough for us to understand what type of iterative adjustments we had to make to our parameters to make the interface really work. So once we figured that out, we ran an additional like 130 participants, which again, you can see over here, the different interfaces. So we introduced the hyperjump in a 3D flying paradigm first. And like I said, there's three different types of input methods that we were looking at. So leaning based, controller based, and seated. So we are trying to compare and see which input method exactly had the benefit over the other. So we use this opportunity to get expert feedback and perform a thematic analysis on all of the participant interviews. So, which the findings of which I'm going to summarize over here. This is the Sankey diagram, just roughly categorizing what we found, like what we inferred from the exploratory study. So that included expert review, which spoke mostly about factors of like learnability, changes we could make to the interfaces to make them more learnable, height management, spatial boundaries, more technical stuff like collision systems and the sensitivity. And we used all of these inputs to make design adjustments to the studies moving on, and we made refinements to the thresholds, visual feedback enhancements, and just enhanced control precision. And most importantly, we decided on an input method. We decided on just the controller based because we found that it had the most accessibility. Uh, Often people were not able to work with the leading interface, and it was a bigger user risk. So yeah, that was the findings from the exploratory study at SIGGRAPH. And we continued this work with like extensive pilot studies at SFU. So I ran 45 participants in total. And in this range, I kept iterating between different pilot tests and using that opportunity to make design changes. We had 24 usable participants at the end. Um, Unfortunately, this iteration did not show strong effects of sickness. There was very limited measures that we were measuring, so we expanded that, and a low usable participant count, so the results weren't strong, and other task design flaws. So to tackle this, we approached it by adding a few features. So we added a jump disable switch, which will make more sense later on. This is to add more agency, which is something a lot of participants were talking about. We also added refined audio visual cues to add more affordances, increase the checkpoint altitude variability, and use a comparative TLX matrix to avoid retrospective bias, which was happening when with our questionnaires. And finally, we had a weighted penalty system to sort of promote the fact that they need to be precise and accurate with the task. So we used all of these all these inferences from both of our exploratory studies, and finally designed 4 interfaces, which were specifically designed for 3D flying. They all use controller-based input. So the way they would work is the right controller would generally be used for speed, which is the right trigger, and orientation is controlled by simply pointing where you want to go. And this is accompanied by a visualization specifically for 3D flying, which is the future me visualization is what we call it. This includes a prediction bubble on top, which is your future position, a height matched avatar to like help you feel embodied, and a vertical beam for depth and height perception. Again, this will make more sense when you see the videos coming up. So yeah, the 4 interfaces, again, to summarize, it's called as so. So continuous motion and manual teleport are common interfaces. They already exist in the space. So these are just redesigned traditional interfaces. We tried to make them specific for flying, because as you know, like teleportation is usually used for ground-based travel. And on top of that, we introduced the novel interfaces. So automatic hyperjump and manual hyperjump, trying to introduce something new and compare them between the 4. So among these 4, the manual hyperjump and teleport, they use they use manual activation. So you activate your jumps or teleports manually by pressing on a physical button. Meanwhile, the continuous and automatic hyperjump use a single trigger speed control. So they're comparable in those ways. So just keep that in mind. So how does this work? So I'm just gonna quickly go over each of these interfaces and like try to understand how exactly they function. So the continuous motion is simply just smooth continuous movement. So as you can see here, once you start moving, you have no breaks to your motion. It's embodied first person motion, so that allows you to have depth perception. There's no sort of audio or visual aids and completely relies on controller based. And then for the automatic hyperjump, you can hear sort of rhythmic cue that's playing right now. So this is a 60 beats per minute music that we just developed, something which helps you stay on beat and predict when the next jump is going to happen. The way the automatic hyperjump works, you can see is that the future me prediction shows up, and starts contracting its bubble every 1 second. And every time that happens, you jump forward to where the prediction visualization is. And what you're seeing now is the jump switch disable. So on pressing down on a button on the left controller, you can disable the jump. And this is something we added again from the exploratory studies because there was mention of like a lack of agency with this interface. So yeah, that's the automatic hyperjump. And moving on to the manual hyperjump, way louder. 1 second. Sorry. Okay. It's really loud, so I'm just gonna
Don't
talk
worry.
about it. Yeah, I'm just gonna talk about it here. So the manual hyperjump uses the same concept as the automatic hyperjump. So it's using the prediction model, but instead of jumping you forward every 1 second, you press the button on your controller, and you have manual control over when you move forward. And meanwhile, the teleportation is also something which is novel, which is we came up with uh, an idea of how it would translate to 3D flying. And we do that by allowing for aim-assisted teleportation. So you can aim your visualization where you want to go in 3D space. And if you're close enough to the target, we'll snap you in place. So yeah, so that's the four interfaces side by side. Moving on to just an overview of all the measures that were collected. So independent variable, obviously comparing between the four interfaces that we just spoke about. We also looked at kind of like order effects, so condition order or trial number. And among behavioral measures, so anything that is more objective, so performance metrics of just how fast they performed in the experiment. So this included just like any sort of errors, missed targets, time taken, temporal dynamics. This is mostly exploring the progression of measures within a trial. So anything that they told us, like how sick they were feeling or how difficult they found it, we were tracking it over the course of each trial. So you can see progression effects. And for subjective ratings, we look at ratings and questionnaires, the simulator sickness questionnaire, and the fast motion scale questionnaire, and other Likert scales for measuring self-perceived motion sickness levels, and also task load and user experience. So we use the NASA TLX, which is a task load index questionnaire. Also looked at ease of use, ease of learning, etc., all Likert scales. And finally, we ended it with a interview, which was open-ended. So the general experiment design involved a pre-study questionnaire, and then you focus on a 5 to 7 minute trial each. So that includes a tutorial phase where they learn how the interface works, and then they apply what they've learned in 3 repetitive segments. And once they're done with each trial, they do the questionnaires that I just spoke about, and finally conclude with a 15-minute interview. So all of this amounted to roughly 90 minutes. And overall, we approached it from a 1x4 within subjects design. So for the participants, uh, we ran a total of 32 usable participants, so 17 male, 15 female. There was a decent mix of how susceptible they feel. We did also have like 13% of new VR users, so that was a good mix. For the equipment, we just used like the latest MetaQuest 3. The whole experience was set up to be wireless using the Airlink, and it was running through Unity. So the setup, the way that would work is we had participants stand on the V-Balance board in a well-lit room with their footprints so that their stance is consistent across all of the participants, and a foam pad and controller straps just for their safety. The idea here was, again, to let them be fully free, but also maintain their posture looking forward throughout the experiment. For the environment, we're using a licensed environment from GeoSim Cities, so it's a large-scale one-to-one model of Vancouver. We've also added this snow particle effect that you can see over here, which helps increase the optic flow. So we're trying to simulate what would be the maximum sort of optic flow you would feel in such a large-scale environment. And again, it's realistic and to scale, so it's very familiar. And the way the path would work is, like I said, there's a free flight where they would learn how the interface works. Then they practice in this tutorial segment. So the tutorial segment goes to 3 turns, and it's situated 100 meters up in the air, so you don't feel as much of the action. And then you get reset back from here to here, and then you do 3 individual trial segments, and that would end the length of the trial. So to understand how this looks, you can just quickly see at the checkpoints. So checkpoint is the primary task that we had. So the participants have to collect these checkpoints and move forward. So there's a sky beam for visibility, so you can see it from far away. There's an artifact in the center, so you aim for that. And translucent bubbles to help you like guide yourself to the center. So you collect them, and each time you interface with the checkpoint, you are stopped, and you need to dwell for a 0.5 second length. So you can see this through a visual and the sound that you just heard. So you hear the audio cue, and you have 0.5 seconds for this meter to fill up. This helps us uh, this helped us basically have the participants have variable speed, so they had different levels of optic flow coming in. So yeah, moving forward, once you reach a corner of the path, you have to turn around using the snap rotate. So again, you just flick the controller on your right and to the direction of the directional arrow, and it implements this 3-step turn, and you move forward with your trial. So yeah, just for time's sake, I'm just gonna move forward. Um, and yeah, then another aspect of the task design was weighted penalties. So the speed at which you enter the checkpoint is noted, and if you don't dwell for the 0.5 seconds, or if you miss the target center, you get pushed back by a distance proportional to your entry velocity. So this is an example here where I went pretty fast, so I got pushed back a decent amount. If I was going pretty slow, I would be pushed back a lower amount. And yeah, that's pretty much all of the task requirements. And once you reach the end of a segment, which is right here, we brought up a few in VR questionnaires. So this is a forced choice question, making them choose if they're feeling any signs of cybersickness whatsoever. And all of it was manually entered by the experimenter, which is me. And once they enter the forced choice question, then talk about just on a scale of 0 to 10, how sick they're feeling. So Likert scale, to like understand the intensity of how sick they're feeling, and then a similar scale for spatial disorientation, and another scale for task difficulty. So once all these questionnaires are answered, we present participants with this leaderboard. So sort of to promote like a gamified idea of competitiveness, and have them actually feel motivated to go through the tasks fast. So this included 3 pilot study participants that we ran, which were doing the exact same segment and exact same condition. We also added to it my score, which is the experimenter's top score, a sort of a score to beat. And finally, you would see your own score to compare yourself with. So this gives them a self-perceived idea of how well they did, and try to push themselves forward like faster in the next segment. So yeah, that covers everything with the task design. So just moving into the results, I just want to give a heads up of how all of the plotting and all of the labeling works. So any plots that you would see, they're all results of ANOVA tests, and they've been tested for assumptions. And so pairwise significance follows the structure over here. The gray dots are data points. The means are with the diamond star over here, and all the error bars represent a 95% confidence interval. And this color scheme will remain throughout any of the graphs that you see if you don't see any labeling. And we'll be using those conditions. So we'll start with the performance metrics. So how did the interfaces perform objectively? So that's the time taken for each for the entire study. So we split that up into the tutorial, the main trial, and then overall time taken for the combination of it. And we can see we basically saw that the automatic hyperjump did the worst. It was significantly slower compared to all the other interfaces. It was less so in the tutorial, but even more so in the actual trial and overall. So between the other trials, there was a relatively similar performance, but the automatic hyperjump did straggle behind quite a lot. Um, and in terms of accuracy and missed targets, there was no significant effects found. There was sort of a trend with the error being more for the teleport, but not significant. In terms of temporal dynamics, so were there any progression effects? So within each trial, how did the effects progress? So for cybersickness, which, as you saw, there was a forced choice question, which is, are you sick? This detects the onset of sickness. And over here, we saw a clear pattern of the continuous motion being significantly higher. This is both in the onset question, the forced choice question, and also the sickness rating. So the 10-point Likert scale also showed that the continuous motion was significantly more sickness inducing than the other interfaces. And the spatial disorientation did not show this effect as much. However, both sickness and spatial disorientation did worsen over the course of the events. So you could see the tutorial, segment 1, segment 2, and there were definitely, it was worsening compared to the actual tutorial. So you can also see the segment 3 is not counted here because we lost some data there, but we did have that for the time taken. Um, I did not talk about task difficulty. So task difficulty did go down. So it was significantly lower for the continuous motion, but across all interfaces, it did significantly get easier to perform the tasks over the course of the 3 segments. And yeah, finally, for time taken, the automatic hyperjump, again, even temporally, takes much more time. But we also saw a performance boost between the tutorial and segment 1, which had they had identical paths. So it showed that there was improvement after learning in the tutorial for the same distance. Moving on to subjective ratings in terms of cyber sickness, we measured using the simulator sickness questionnaire. We did not see any clear effects for the total score, although one of the subscales did show a significant effect for the continuous motion being worse for disorientation. For the total SSQ, we did see a similar trend with the continuous being having
Kenneth,
a worsening.
quick interruption. So
Yeah.
somehow there seem to be some black windows covering the results. I'm not sure if that's
Oh,
just
that's
an oversight.
probably, I think it's probably Zoom.
Yeah,
Is it
there
gone
might be
now?
some issue. So maybe,
Is it fine now?
yeah, there's one at the top right left.
That's also Zoom.
Yeah.
Okay. Okay.
Okay. Yeah. Do you want to go back to the last slide?
Oh, okay. Sorry.
Yeah. We'll just get the extra minute or two. Sorry, that was a Zoom issue. Thanks.
I'm just gonna go. Okay. So, well, progression effects, I guess, yeah, this part was probably covered on the side. Um, just gonna go a little ahead. Yeah, so time taken between the interfaces temporally did show that the automatic hyperjump was worse. And there was, however, improvement between the tutorial and segment 1. I'm also just, since you guys couldn't see it, I'll also just go over the performance metrics really quick. Um, yeah, just again, there was worse times for the automatic hyperjump and no significant effect for the missed targets. Also, we can come back to this if there are questions later on. Let's move forward. Yeah, the other thing that I missed out was task difficulty getting easier. Okay, so yeah, the subscales I covered, so I'm just going to move on to the Likert scales. So the 11-point Likert scales that we asked post-trial included I felt sick, I felt dizzy, and I felt spatially disoriented. And across all 3 of these, we saw that there were significant effects. For sickness and dizziness, the continuous motion interface did cause more sickness and dizziness than all other interfaces. For disorientation, the automatic hyperjump caused more like marginally more disorientation compared to the teleportation interface. And for vection intensity, for the sense of like self motion, continuous motion again produced the strongest sensation of self motion. This is as expected from like existing research. This also, as you saw earlier, correlated with the higher cybersickness experienced. In terms of the teleport, which again we expect to have lower vection intensity, that was true. Although we did see a above average vection intensity for the teleport in general, which was due to iterative jumping, which was covered later in the interview section. And yeah, in terms of task load, so we used the NASA TLX. So mental and temporal demand showed significant effects for the automatic hyperjump being worse than the continuous. No strong effects between any of the others. Same applied for performance and frustration. Participants did rate the automatic hyperjump as less performant and more frustrating compared to the continuous motion. There was also higher frustration levels overall, the worst frustration levels overall with the teleport, sorry, the teleport is here. The teleportation, which just likely was due to the consistent requirement to aim to the targets. Um, yeah, and then moving on to other subjective ratings for like how present and immersed were they. So continuous motion again had significantly more presence and plausibility. So they found that the events and the environment overall were more believable in the continuous motion interface and felt overall lesser breaks in their presence compared to the other interfaces. So that just shows that the teleportation and sometimes the automatic hyperjump would cause more breaks in presence, and across the board, the teleport did have lesser presence and plausibility. Um, and moving forward to learnability and usability. So we had a Likert scale for ease of use and ease of learning. And we saw, again, the continuous motion was the easiest to use and to learn. And the same applied for the teleport. So, which again can be explained by the fact that these are traditional locomotion techniques. There's more familiarity with them. They fit a mental model. So the novel techniques did lag behind significantly with in terms of learnability. And for ease of use, everyone like it was significantly clear that the continuous motion was easier to use than all the other interfaces. We also checked for order effects because we were interested to see if there were any carryover sickness effects or any fatigue buildup. There was no significant effects for any of the sickness measures. So there were slight trends of increasing sickness across the four trials, but not strong enough. For order effects related to the physical demand and performance, however, there were significant effects from trial 1 to trial 4, showing that there was a fatigue buildup likely for explaining the physical demand, and for performance, likely because of learnability. This is again validated by the fact that if we see the actual performance between the four trials, there was a significant increase between the first trial and all of the other trials. So this adds up. For all the other interfaces, so all the other measures, we had just consistent cognitive load across most measures. So these were the only ones that stood out. And we also had them rank the four interfaces according to three different categories. So how sick that, like in terms of experience sickness, so which one's best for sickness would be number one. What was their overall preference and comfort? For comfort, we didn't see any strong effects, but for the other two, uh, by just simply combining the first and second ranks and third and fourth, we get a clear image of which interfaces were preferred and which weren't. And you can see that for overall preference, the manual hyperjump was actually pretty closely tied with the continuous motion. And this was significantly different from the teleport and the automatic hyperjump, again, having a similar sort of preference rating. For sickness, the teleport, you can see by far had a lead with the first two ranks. The manual hyperjump is a close second, and the continuous and automatic didn't perform as well. So that's subjective rankings. And finally, thematic analysis. There's more depth in this if anyone needs to ask questions, but I'm just going to go over the overarching themes that we figured out. So presence, fun. So for presence, participants consistently spoke about the teleportation disrupting their immersion and continuous motion feeling more immersive, but also causing higher cyber sickness. There were a lot of mentions of agency enhancing presence, and also that elements of music and audio cues contributing positively to the sense of presence. There's also increase in frustration was associated with like detracting from the experience. So that was a negative. Um, and for cyber sickness, again, continuous motion was most frequently mentioned to cause sickness, especially when they were moving at faster speeds. Some participants did use strategies to tackle this. They tried closing their eyes and mitigated the symptoms, but they still had to do so because there was already an onset of sickness. Um, and finally, preferences. So control and immersion were very often mentioned as their key motivators as to like how they ranked them and how they preferred the four interfaces. So familiarity with the techniques did influence the ease of use and comfort, as we would expect. And so, yeah, summarizing all of the results into a sort of strengths and weaknesses chart, you can see that the continuous motion provides higher presence and immersion. It's easy to learn and easy to use. It's also fun to use, likely because of higher erection intensity. And meanwhile, it has negatives of higher sickness symptoms and more of a dizzying effect. The automatic hyperjump did have lower cybersickness symptoms, but not strong enough. People often mention that it would be effective for simple exploration tasks rather than precise tasks. And the negatives were that it performed poorly. People often mentioned the requirement for more agency and experiencing disorientation. The manual hyperjump was overall a more balanced interface. It had the positives of both the continuous and teleport, offered the agency that was missing from the hyperjump and the automatic hyperjump, but unfortunately no standout strengths, so no objective number ones that it was able to achieve compared to the other four. Um, yeah, and then finally the manual teleport, low sickness symptoms, but um, like very not immersive and incredibly frustrating. So yeah, to conclude with the four interfaces over here for your reference, you can see that the continuous with its smooth continuous motion had higher presence, but this type of motion caused a more severe sort of cyber sickness with progression. The automatic hyperjump, better for simple VR tasks, but requires more control. The manual hyperjump being a balance of everything, and the teleport being the most suitable for anyone having like high sensitivity to cyber sickness. We also, going back to the research questions, we also established that the leaderboard interfaces were often mentioned to have like to definitely promote competitiveness and engagement. The rhythmic motion, so the rhythmic music contributed positively to user experience, and novel methods were harder to learn than traditional methods, as we saw earlier. So the limitations of the work done here mostly has to do with the fact that obviously this was a relatively small sample, so it's 32 participants. We could have run more to create strong effects. Control sensitivity and haptics. This was a very frequently mentioned topic, just the fact that the sensitivity didn't work for them, so maybe adjusting it for future studies. Haptics would definitely help providing better feedback and affordance as to when the interface switches between its different modes. The trial duration, as you saw, was just 5 to 7 minutes, and that wasn't enough for people to feel strong sickness effects sometimes. And then the speed comparison confound is uh, between the two manual interfaces and the automatic interfaces. There was a difference in terms of how frequently, how fast you can move. So the top speed did depend on how fast you press the button. So there are some minor confounds over there. And finally, fatigue buildup being just as you saw over the course of the four trials, there was a buildup of fatigue. Oh, I guess I missed the task context. So yeah, task context bias also showed that basically the findings may not generalize for all situations. There was often a mention of different contexts and different tasks being which would lead to a different sort of preference and ranking between the four interfaces. So that's something which could be studied in the future. And that's it.